we now discuss an application of Rolle's theorem from the section Differential Calculus, and it is meant for joint entrance examination main aspirants. The result is, we call it as the result A. Let f be a real valued function defined on the open interval a comma b, and it is a twice differentiable function. If the equation f of x is equal to 0 has n distinct roots, then the equation f prime x is equal to 0 has at least n minus 1 distinct roots in the open interval a comma b, and the equation f double prime x is equal to 0 has at least n minus 2 distinct roots in the interval a comma b. So f is a real value function defined on the open interval a to b, and it is a twice differentiable function, and it is given to you the equation f of x is equal to 0 has n distinct roots. Then we have to prove the equation f prime x is equal to 0 has at least n minus 1 distinct roots in the interval a to b, and the equation f double prime x is equal to 0 has at least n minus 2 distinct roots in the interval a comma b. This is a very important result, and using this result we have established a result that has appeared in the JEE examination, that I will tell you at the end of the proof of this result. Let's now recall Rolle's theorem, which we will be using in the proof of the result. If a real valued function f is continuous on the closed and bounded interval a comma b, differentiable on the open interval a comma b, and f of a is equal to f of b, then there exists at least one point c belongs to the open interval a comma b such that f prime c is equal to 0. It's a very well known result, and we have been using it quite a good number of times. Now this is our result, what we wanted to prove, and it is very important. Let's see the proof of it. We have f, a real valued function defined on the open interval a comma b, and it is given that f is differentiable function. Given that the equation f of x is equal to 0 has n distinct roots in the open interval a comma b, let's call those roots as alpha 1, alpha 2, alpha n. That implies alpha I not equal to alpha j, I not equal to j, implying alpha i's are all distinct, and f of alpha I is equal to 0, saying alpha I is a root of the equation f of x is equal to 0. These are all otherwise called the zeros of this equation. Now arrange these alpha i's in the increasing order. Let alpha 1 less than alpha 2 less than etc. less than alpha n. Now note that f is differentiable in the closed and bounded interval alpha 1 comma alpha 2. Why? Because alpha 1, alpha 2 are elements in the open interval a to b, wherein it is f is differentiable. Therefore f is differentiable on this. Therefore f will be differentiable, and f will be continuous in this. And f of alpha 1 is equal to f of alpha 2 is equal to 0, because alpha 1, alpha 2 are the distinct roots of f of x is equal to 0. So you can use the Rolle's theorem. Now, by Rolle's theorem, there exists at least a point beta 1 belongs to the open interval alpha 1 comma alpha 2 such that f prime beta 1 is equal to 0. That means beta 1 is a root of f prime x is equal to 0. Now, by similar argument, there exists at least a point beta 2 belongs to alpha 2 comma alpha 3 such that f prime beta 2 is equal to 0. That is, beta 2 is a root of the equation f prime x is equal to 0, and clearly beta 1 is not equal to beta 2. Continuing in this way, the last interval alpha n minus 1 to alpha n, there will be at least a point beta n minus 1 belongs to the open interval alpha n minus 1 comma alpha n such that f prime beta n minus 1 is equal to 0. That means beta n minus 1 is a root of f prime x is equal to 0. In all, how many roots we have got? So, thus the equation f prime x is equal to 0 has at least n minus 1 distinct roots, beta 1, beta 2, beta n minus 1 in this open interval a to b. Now concentrate on beta 1, beta 2. Beta 1, beta 2 and f prime is f prime x is differentiable on the closed interval beta 1 to beta 2, and f prime beta 1 is equal to f prime beta 2 is equal to 0. You apply the Rolle's theorem, then there exists at least one point gamma 1 belongs to the open interval beta 1 comma beta 2 such that f double prime gamma 1 is equal to 0. So continuing in this way, we will get gamma 1, gamma 2, gamma n minus 2 distinct roots for this f double prime x is equal to 0. So from this, it now follows as in the previous, as the above argument, the equation f double prime x is equal to 0 has at least n minus 2 distinct roots, which we call them as gamma 1, gamma 2, gamma n minus 2 in the open interval a to b, where gamma 1 belongs to beta 1 to beta 2, gamma 2 belongs to beta 2 to beta 3, gamma n minus 2 belongs to beta n minus 2, comma beta n minus 1. So hence the result. So thus we have proved there will be at least n minus 1 roots for the equation f prime x is equal to 0, and there will be at least n minus 2 roots for the equation f double prime x is equal to 0. Hence the result. You note down that these roots beta 1, beta 2, beta n minus 1, gamma 1, gamma 2, gamma n minus 2, they are all distinct. They are all distinct. And that is the detailed proof of that result, and that result is very, very important. And I will tell you that result we have used in this question, in this problem. This problem appeared in JEE Main exam held on 27th July 2021 in the second shift. This is the problem. Is the problem f is a twice differentiable function, a real value twice differentiable function defined on the open interval a to b, and fx is given to be integral a to x g of t dt, where g of x is a differentiable function, and if f of x is equal to 0 has exactly 5 distinct roots in a comma b, then g of x into g prime x is equal to 0 has at least how many roots? So these are the options given to us, and f of x is given to be f of x is equal to 0 is given to be having exactly 5 distinct roots. So wherein we will be applying our result A. So we will use that result A here, and the option 2 comes out, that is the 7 roots, at least 7 roots will be there for g of x and g prime x. That will be coming out as an answer for this question. For a detailed proof of this problem, please see this following earlier video. This is the earlier video we have. So that is the discussion of the solution of a result, the application of Rolle's theorem. I hope that you have understood the solution of that application and work out some more applications on Rolle's theorem. I wish you all the best. Thank you.